Right. So this is a joint work with BP Castagna, which is here in the room. This talk is going to be about type systems, and in particular, type systems for dynamic languages. So think TypeScript. In our case, we are working with a team at Elixir to develop a static type system for that language. This is what motivates this work. So if you've seen the keynote of Christos Dimoulas on Tuesday, you might remember something like this. And basically, the point is to say that if you want to be able to type a program in JavaScript, for instance, you need a number of features. So you need set-theoretic types, union, intersection, and even negation. You need subtyping, you need polymorphism, occurrence typing, and also gradual typing. In this talk, we will have all these features except gradual typing. We do have gradual typing in Elixir, but this is a kind of orthogonal to what we do here. So in particular, to give you intuitions, we use unions to type branches, so like if then else and these kind of things, and also occurrence typing. We use intersection to give overloaded types to functions. And we use negation to type, for instance, case expressions. So in this talk, what I will talk about is extending the type system that we have with a polymorphism which is specific to records. So our approach and the way in which the way in which it differs from TypeScript, for instance, is that we design type systems that are sound by design. So we have a theoretical framework that we call semantic subtyping, which will give us the tools to derive type systems that are well adapted to dynamic languages and programming idioms that we can find in such languages. So the problem is that, well, record types are really important in Elixir, for instance. And if you want to be able to type check the libraries using records, well, you cannot do it currently with the system we have. So we will need to extend it to support raw polymorphism, which is the specific kind of polymorphism I was speaking about. So a quick example to show what raw polymorphism is. So let's take this function here, which is written in an Elixir-like syntax. This function takes as input a record, which has a field called ID, which has an integer inside, and we just increment this field, the value of this field by 1. So if we want to give a type annotation to this, we will say, OK, I have a record as input, which we denote with the brackets. This record has a field ID of type int and can have any other field. This fact that it can have any other field, I indicate it with these 2 dots here. This is what we call an open record, if you're familiar with it. The output type is going to be the same thing. So now the problem with that is pretty well known, is that if I define a record with more field than just ID, I can apply my function. But then what happens is that this argument here has this type with the 3 fields. And then I can type check the application here because this type is going to be put in correspondence with this one, and we agree on the type of ID, and we agree that there are other fields, but I don't know which one they are. So in the end, my output type, so the type of this element here, is going to be this thing exactly. And then this thing exactly is something that tells me that ID has a type int, but tell me that I have arbitrary other fields, but I don't know what thing they are anymore. I forgot what they are, so I lost some information. So in the end, if I want to use another field from this record, I cannot do it because type checking will fail. So the solution to that also is well known. The idea is to replace these arbitrary other fields by a variable, and this variable just gives a name to the other fields. So I can say what I had at the start is exactly the same thing as what I have at the end. So when I apply my record, what will happen is that I will be able to find an instantiation of the variable to these 2 other fields here, which then, if I look at my function under this instantiation, tells me that, okay, I remember that I had some other fields and there are these ones. So I can apply my projection. So this is the idea of a polymorphism, and this is like a really old thing. So there's nothing new here. So what makes it difficult is that in our framework, as you saw in the first slides, is that we have a lot of different features. In particular, we have these set-theoretic types, union, intersection, and negation. And we have this semantic subtyping. So semantic subtyping is not just the name of our framework. It's also what kind of subtyping we use. And it is a subtyping that is not syntactic, but that is defined through an interpretation of the types. Remember also that our framework already has parametric type polymorphism. So the idea will be to extend the tools that we have already for type polymorphism to row polymorphism. So if I go back to my example, what do I need concretely to be able to type check it? So this is just to remind the types of the function I have and my argument. And now when I want to apply this function to this argument, the thing that I need to check is this subtyping constraint, verifying that the type of the argument is a subtype of the input type of the function. So there are two things needed for this. One thing is to define exactly how to decide subtyping. And the second thing is to be able to find the correct instantiation of the variable row. So first thing, subtyping, how to decide it. And I will start by describing really quickly what semantic subtyping is, what the core idea of it is. And the idea is to consider an interpretation of type in which intuitively the interpretation of a type is the set of the values it contains. So integers will be interpreted as the set of all integers, strings as the set of all strings. And then the really nice thing is that we will interpret set connectives on types as the corresponding set connectives on sets. So union on types is interpreted as union on sets, and so on. So this gives a really intuitive understanding of set connectives on the types. And then my subtyping is going to be defined through this interpretation by saying that a type T is a subtype of a type S if the interpretation of T is contained in the interpretation of S. Right, so to say it again, I start from my interpretation of type, where I find out what formula I need to decide containment of one interpretation inside another. This formula, I lift it to the level of types. So I get a formula that tells me on types when a type is a subtype of another one. And this formula, we can actually refine it into a backtrack-free algorithm to decide subtyping. And here, just one thing I want to say. So I don't want you to understand this. I just want to point out this thing in red here, which surprisingly is the only difference we have between the subtyping algorithm without row variables and with row variables. So adding row variables to our system, just in the end, asks us to add a little check in this algorithm. And this is just checking that the row variable we consider is contained into a finite set. So this is interesting because it means that from the point of view of asymptotic complexity, having row variables or not having them is the same for the subtyping algorithm. So yeah, to type check our example, first thing was deciding subtyping. Second thing is to find a correct substitution for our variables. So this is the unification problem. In our case, we call it tallying problem because we don't have equality constraints, but subtyping constraints. So once again, the idea is going to be to extend the algorithm that already exists for type variables and extend it to row variables. One insight I could give on this is that one important step of unification or tallying is to decompose constraints into smaller sub-constraints. And for this, we use a generalization of the subtyping formula that once again have been, well, we found it by looking at the interpretation of types and bringing it back to the level of types afterwards. So this algorithm is sound. This is good. It is not complete. This is less good. But okay, one thing is that if you forget about set connectives, we are conservative with respect to the usual algorithm of polymorphism. So without set connectives, we are complete. Now, why aren't we complete overall? The thing is, we want to be really precise. For instance, if we look again at our function bump ID here, its type is basically the type of the identity function, right? So if I give it as an argument a type which is a union type, well, I want to get the same type as a return. And this is indeed what our algorithm does. It gives us the union type as a return type for this function. But if we will consider a less general or weaker algorithm that we would hope to be complete, we would rather get something like this, where the union will be smashed. I mean, the union of record will be smashed into a record of unions. And in particular, we lose a lot of precision because you can see, for instance, that the correlation between having an integer here for the tag and having the field com present is lost in this final record. So what I presented before was an extension of the framework of semantic subtyping and an extension of the tools we can have by working on types. So we have a unification algorithm, or tallying, and we have subtyping, and also we have an interpretation of types. But what I showed was independent of the language you could choose. So now what I'm going to do is to define a language and give a type system, and this type system is going to be using semantic subtypings and set-theoretic types and polymorphism. Once again, you don't need to look at the details, but we define a type system. We define a lambda calculus which has records, and it has record extension. It has a deletion of fields on records, and it has projection of fields. And we can show that this type system has preservation and progress. Since it is non-algorithmic, we define an algorithmic type system. So you can notice, for instance, in the application rule, how we need to find a correct substitution to relate the type of the argument to the input type of a function. So this is given by the tallying algorithm. And of course, this algorithmic type system is sound and complete with respect to the first one. So to summarize, what we have shown in this work is that the repolymorphism, which has been around for a long time, is not limited to syntactic approaches to subtyping, but that we can also integrate it into the semantic subtyping frameworks with set-theoretic types, and that it actually fits pretty well because we can extend existing algorithms with polymorphism. And so this is really important for us because there are several implementations. Thank you very much. There are several implementations of semantic subtypings and set-theoretic types in the wild. And it's really important for us that developers can just extend what exists with polymorphism. On the side of implementation, to finish quickly, this is work in progress to implement it in our language, our research language, which is called Cedius. And then once it's done, we would like to implement it inside the type system for Elixir. So I will stop here. Thank you very much for your attention.
Okay, maybe time for one quick question.
Hi, thank you for your talk. Just out of curiosity, and since I think polymorphism can easily support recursive types, especially equal recursive types, is there, after integrated into the semantic subtyping framework, is this kind of easily supported recursive type would it still work?
So we have actually, I didn't speak about it, but we have recursive types. I mean, we work with recursive types already.
Yes. So it still works after you integrate into the semantic type subtyping framework.
Yeah. I mean, yeah. I don't know if it's your question, but yeah, we have recursive types. We only work with recursive types.
Yeah. Thank you.
Okay. Yeah.
Okay, let's thank the speaker.